Good afternoon. So today we will discuss mainly two X-ray based two scattering techniques, that will be small angle X-ray scatterings and which will be small angle X-ray scattering and small angle neutron scattering, both X-ray as well as neutron we will see. In addition, we will discuss little bit about basics of microscopy. So before going to the next class, which will mainly be on electron microscope. So today I'll just discuss the little bit about conventional microscope. But first, coming into X-ray scattering techniques. So first of all, why we need a scattering patterns? If you see, we have a material that you can go for a microscopic length scale as a microscopic length scale. For example, if you go for the macroscopic length scale, you can use optical microscope, light scattering, those type of microscope, or even electron microscope you can use. But for microscopic size, that is, you have a dealing with size is very less, that is 10 to you see 0.01 angstrom. In that size level, mostly proteins, nanoparticles, micelles. So those type of structure you can't able to see all these optical or light microscopy. So you have to go for a technique like X-ray diffraction, electron diffraction. So this type of technique you use for analysis of molecules, nanocomposites, or nanoparticles. Those type of thing you can use this. But if a size is in between somewhere 0.1 to 0.001 in that range, so you have to mostly see some micelles or some nanotubes, nanoparticles. Those you have to use. Other than this electron microscope or the transmission electron microscope, scanning electron microscope. Other than that, two scattering techniques used, that is small angle X-ray scattering and small angle neutron scatterings. So X-ray neutron measurement can't produce picture of particle. Like in case of electron microscope, we used to get a picture of the microscope image. But in the scattering technique, X-ray neutron scattering technique, we will get some data from where we have to interpret, by using some Fourier transform to get the final information. So first of all, the scattering patterns, the advantage of the scattering pattern is fast. The scattering process is much faster. It gives meaningful global average instead of just local, information. Like if you go for a particle size information from TEM or from other way techniques, so you will get mainly that specific some few particles you'll be able to see, and those particles you can measure the size, you can see the structure. But here in case of scattering technique, what you will get this type of diffraction that scattering pattern, and from where you will interpret to get a structure that will be mostly the global information, and can prove buried 3D structure, that sometimes the three-dimensional structure which you are not able to see in microscopy techniques. So those information you can able to get here, and it is an in situ. During your experiment also you can use them. During your synthesis you can use simultaneously your particle formation, that those things you can also see by the scattering pattern. As well as this is a non-destructive techniques and can prove in liquid state. The most important thing is here that you can use the sample as it is in liquid stage. During their transformation, there is some phase change process, something occurring. So those information you can get, including the function device functionalities. So, but the most difficult part of the scattering technique lies in their interpretation. Since here that you have a, you have to transform your data from a Fourier form to the real space. You have to transfer. So then to interpret the data is quite difficult in case of X-ray scattering techniques. So if you see the small angle scattering versus microscopy, so microscopy mainly uses lenses. You have say lenses like this, so that those lenses will use to resolve the real space image. You have an incident beam that fall the sample, then it will go and fall on the lenses, and finally you will get a image on the image plate. So this is mainly that you have a these lenses to get a real space image. But in case of small angle scattering measurements, you have an interference of waves. So here that part is that X-ray or neutron, it fall on the sample surface, then it's scattered. So this is a mainly since scattering technique, so it's mainly based on the generation of waves. So that waves, you will say that how the waves are interfering with each other. So mainly it measures the interference of wave vectors. So if you see here, you have an incident beam falling on the sample, then at a very low angle, it's scattered here. So you'll get, this type of, some this interference wave, and then this is in Fourier space you will get. So you have to convert by an Fourier equation to a real space, and the more information which you get is average over volume. So it's you have average over volume data what you will get from this. So it's mainly used for characterization of nanoparticles, like you have a nanoparticles of size from 1 nanometer to 100 nanometer. In that range, you can able to get that size determination. Also, you can use the interaction among the molecules, like you have a molecules, a nanoparticle or a protein that you have. So those the interaction among themselves, as well as interaction within the particles, as well as with another particle. So those information you can get, and you can study the structure of cell parsing. Like some materials, if you see, like for example, micelles that forms from surfactant molecules. So the surfactant molecules self-assemble themselves to a spherical or an elongated structure. So those type of information we'll able to get. In addition, investigation of multi-component systems, like you have a multiple system, like for example, you have gold coated with CETAP, or is like acetyl ammonium tetramethyl ammonium bromide, like those type of surfactant molecules coated on the surface. You'll be able to get both core and cell information using this type of both combination of neutron and X-ray scattering techniques. So if you see the small angle scattering techniques is that you mainly uses neutron and X-rays here. That is a powerful technique to study the structure and dynamics. You will get the structure of the system as well as its dynamic behaviors. So a wide range of length scale of 1 to 100 nanometer, and a different time scale you can able to measure. If you see this right image, so in the neutron, this X-ray scattering here, in case of X-ray scattering, you can see the first image, you can able to see the bone structure. Because those materials which has dense, like high jet material, those things, you'll be able to get, X-ray pattern, because they inhibit the X-ray and finally produce a shadow image on the photographic film. But in case of neutron scattering, if you see here, you can get the both here in the tree structure that I have drawn here. So both bone that as well as leaf structure. So you can get that this leaf structure as well as the hard bone structure. That means so you can able to detect both soft material as well as hard material. So both things, that low jet as well as high jet, both things can be possible using that neutron scattering technique. So neutron scattering is mainly due to, as I earlier discussed, is mainly due to neutron interaction, nuclear interaction. That is one thing. And second one, that magnetic interaction, since that electron has an unpaired spin, so that electron, this neutron interact, so you'll get a magnetic interaction. But in X-ray, it's mainly interacting from the scattering from the electrons. So the basic difference is that it's a nuclear interaction, but it is an electron interaction of X-ray with the electrons only. So small angle X-ray scattering mainly use X-ray, that electromagnetic radiation, and that is probably expressed in terms of electron density. If you have high jet material, that means the electron density of that material is high. So based on that, you will get a particular image. But in case of neutron scattering, that uses mainly neutron particles. So here, instead of electron density, you have a scattering length density. That we'll see how the scattering length density will depends of the defined material. The atoms has different scattering length density. So it doesn't depend upon the jet value. So it's randomly variation of the length density that measures how much the scattering occur on a particular material or particular atom, that that's scattering of the neutron occurs on a particular atom. So if you see the history of small angle scattering and its parameters, if you see first in 1930, that Gunnier has introduced the small angle scattering techniques, but from 38 to 50, so different fundamentals and theories and all these things were developed. But later on, the first experiment was performed in 1950 using the experiment with protein molecules. So the protein structure was first analyzed in 1950, but the use of SAXS increased with user-friendly after different beam lines that adopted method like different this high energy beam lines are once developed, so then only it become more popular. In the mid 90, the papers from publication from the small angle scattering increased. So it's mostly get popularized during 1990s. So we can measure different parameters here. So here you can see what you will get from a spectra, that intensity I, that is you express in terms of IQ. So Q is wave vector versus Q. So the X-ray diffraction, what you use 2 theta, you use over here, that since a very small angle, that theta is very small angle, we use Q here, that wave vector that I discussed, that Q wave vector. So from the intensity versus Q, that we get how the intensity is varied with respect to the Q. So those we get, and then we have to transfer it to Fourier transfer, we get the real data. So it's used mainly, you can measure the size of the scatterer. So that means the particle size you can measure, amount of what is the concentration of the particles that you can show, and polydisperse, the variation in the size of the particles, and shape of the scatterer that you can get, that is morphology as well as composition. So all these parameters you will get simply from a small angle neutron or X-ray scattering. It's mainly used for size, shape, polydispersity as well as composition. All these information you can get here. As I told, here in small angle X-ray scattering we use Q, that wave vector Q, instead of it's theta. So this Q is nothing but 4 pi by lambda into sine theta. If you see here in small angle X-ray scattering, we will mainly use coherent, that is in phase elastic scattering radiation at small angles. So you have an X-ray beam or neutron beam, it comes and falls on the sample, and then it's scattered at a very small angle. You can see this angle is quite small. So if you see, this is the scattered one, this is the transmitted beam. You saw here, which angle is very, very low. So that angle is mainly 0 to 10 degree. Generally, this is the very, very low we use in this case. So here that incident vector k and the scattered vector k dash, if you just Q vector, that Q equal to k dash prime minus k. So you can get that Q equal to 4 pi by lambda sine theta. So here that those incoherent inelastic scattering, they will give some backgrounds, but that we don't consider. Mainly we use here for measurement, we use coherent in phase elastic scattering. So scattering experiment measure the number of neutron or X-ray scattered at different values of wave vector. Like a different value that you have a wave vector of this. So at a different wave vector, like you changing the angle theta, by varying the theta, you will get different wave vectors. So Q. So since if you change the theta, so you'll get different Q. So those Q is measure the number of neutron are scattered at different Q value. So that we are measuring mainly. So Q is here 0.0012 to 1 angstrom inverse, and scattering from particle to 1 to 100 nanometer. If you see the relation between a small angle scattering technique to a diffraction, so they are interrelated. If you see that wave vector k, that k equal to 2 pi by lambda, and you can see your k and k prime here. So this angle will be 2 theta, and if it will make a right angle here, then it will find out the equation Q equal to 2k sine theta. Is k is equal to 2 pi lambda, so the final equation equal to Q equal to 2 pi by lambda sine theta. But in case of diffraction, you have n lambda equal to 2d sine theta. That Barick's equation will satisfy for a diffraction to occur. So that you can represent as 1 by d. If you write is d in one side, so n lambda by sine theta equal to 2d. So then you take 1 by d, you reciprocate inverse it, that you take d this side, and then in final equation you get 1 by d equal to 2 by lambda sine theta. So if you see this is these two equations, then Q equal to 4 pi by lambda sine theta, and 1 by d equal to 2 lambda by sine theta. If you see there is a 2 pi term which less here. So then it will be d equal to 2 pi by lambda. So these are Q equal to, so that means Q equal to wave vector Q equal to 2 pi by that this spacing. So they are in small angle X-ray scattering and diffraction are interrelated, that you can say. So you need mainly that small angle X-ray scattering. You see that here you have a smaller particles and you have a bigger particles here. So these are two types of particle I have shown, but when I have a smaller particle, so there you have a scattering angle is greater than 10 degree that you use in case of diffraction. You will get the lattice interference between the lattice plane, and those type of information we will get. So D is here less than 0.1 nanometer. But in case of bigger particle like if a large particle, that means you have to go for a very here, since a smaller particle, big particle of theta is quite large. But here, in case of bigger particle, you have to go down to smaller theta to get, say that theta is 0 to 10 degree, you to get information about 1 to 100 nanometer. That means bigger is the distance in this equation, d equal to 2 pi by lambda q. So bigger is the distance, smaller is the q. So the bigger particle, to see this big structure, your theta has to be very small. So that's why we have to go for very small theta. You can see here, if a high Q, that wide angle, normal X-ray diffraction technique, you will see interparticle, the atomic level data. So you have to get very small information here. But in case of low Q, that is a small angle, since you will see theta is inversely proportional to Q, sorry, lambda is inversely proportional to Q. In that way, that and this way small angle, that means you have a Q is very small. So Q is directly proportional to theta. So that Q, you have a small angle, so you have a low Q, so you'll get the whole information about the whole structure, all these things. So larger the structure, the smaller the scattering angle you have to take. So if you see this copper K alpha that we have shown here, so D and 2 theta relation, you will see when D you have a 10 angstrom, that means Q equal to 0.628 angstrom inverse. So when you go down the D, if you increase the D to 0.001 micron to 1 micron, you can see how theta is decreasing and corresponding Q is very low in this case. So high angle X-ray scattering that usually 10 to 160 degree will give you information about atomic scale structure, mostly lattice parameter and those type of things you will get. But you have a small angle scattering, so you'll be able to see the big structure. So in case of small angle X-ray Newton scattering, your Q range in between 0.001 to 1 angstrom, and then you are able to see a 2 theta, the very small angle 0.1 to 10 degree, you will be able to say the whole structural information of the particle. So if you see the neutron and X-ray wavelength are equivalent to the space between atom and crystals. So why you are using this in the X-rays and neutrons? Because that the interatomic d-spacing of an atom is equivalent to that of X-ray and neutron wavelengths. So you have to go for a very large theta, very large, high theta value, will be able to see those interatomic space and all these things. So you can see here, this is the wide angle X-ray structure that is normally used in X-ray diffraction. So you can see that high theta value here, you will be able to get this information. But you have to go to low theta, you will get whole set of this experiment, this information that you will get in the interparticle interaction, you will say size of the particle and surface structure. So those information and form of particles, those information you will get. So it gives diffraction peaks at high angles corresponds to atomic position. However, a large structure, if you go at larger structure scattered at smaller angle, and so that's why you can get information about fibers, polymers, surfactants, dispersion, nanoparticles, liquid crystal, only biological materials. So those materials, structural information you can get from this. So for technique of small angle, use material properties rather than atomic properties. Like for a large Q value, that is very small angle, you will be able to get, so the small Q range and small theta value, you will be able to get a material properties mainly rather than that atomic property which you get in case of XRT. In case of XRT here you can see you will be able to get atomic properties, but in case of small neutron X-ray scattering you will get material properties. So if you see the experimental parts, you have a light source here. From the source the X-ray will come and fall on the monochromator or the chopper that we call monochromator, then we pass through different collimating optics and then we fall in the samples. So from the sample, it's scattered at a very low angle, which is almost parallel to the incident beam. So you have a detector here, So that detector will collect all the data and you'll get a pattern. So here in the center, you used to put a beam spotter to prevent that detector burnout because of the direct beam. And here the source is mainly X-ray generator. You can use for the source for X-ray, or you can use synchrotron based technique for X-ray. But in case of neutron, you have to use reactor source or a spallation. So this is for neutron and this is for X-rays you have to use. And the monochromator is, they will separate particular defined wavelengths will allow, and collimating optics, you have defined divergence beams and those type of, with maximum beam size that will be reduced by this collimating optics. And then you have collects the radiation, the detector will collect the radiation, generally mostly in case of this, you use a 1D detector that or a CCD, charge coupled detector, a photographic film type detector you use in case of this small angle X-ray scattering, so that you have a 1D or 2D that detectors there. So distance of the sample and detector you use to measure, and then the wavelength determines the size range measured. Like whatever the size you may want to measure, so that will be mainly decided by the sample to detector distance, the sample to detector distance, as well as the wavelength mainly determine the size to be measured. That the instrument's capability to be decided by this, how far is the sample and detector distance, as well as the wavelength of the particular instrument we use. So in case of small angle X-ray measurement, that you have provided a scattering cross section per unit volume, like I0 is the intensity of the initial X-ray beam or neutron beam fall on the sample surface, then will interact and then it scatter. So you have to measure this particular, volume element, that cross section per unit volume, how much area is interacting, and corresponding the scattering that you are getting that per unit volume. So if you the scatter intensity for solid angle, that di by d psi equal to transmission parameter and I0 intensity, and d the thickness of the material, and scattering cross section per unit volume, that expressed in centimeter inverse and steroid inverse. So mainly, so this di by d psi will measure, the scattering intensity for solid angle. So that scattering intensity for solid angle we used to measure in this case. So if you see the theory, the incoming wave scattered of the electron cloud, in case of X-ray, it's that incoming wave, that incident wave scattered from the electron cloud. You have a nucleus here, and you have an electron here. So incoming X-ray will be scattered back from this electron cloud, whereas the incoming neutron it will scattered from the nuclei. It is from the nuclei. This is case of neutron, and this is case of X-ray. It starts from electron. This will be the nucleus. Okay, so interference of scattered wave from a material added up, like one wave will come and scatter this, another wave come and scatter this. So interference of this wave will give you a net scattering that will be expressed in terms of amplitude. So this is what will get an intensity I Q. You will get that will explain the parameter called scattering intensity, total intensity. Then you have to do Fourier transform of the structure. You have to get the real information. So the measured intensity is the magnitude will be square of the amplitude. So IQ equal to, if you express that the volume in which it interact, and this rho r, that is density of that particular material at a distance r, that electron density of a particle of a volume v in a fixed concentric fixed element or something, that will get that rho r, that electron density into e to the power minus IQR by dV. dV, that particular volume, that cross-sectional volume that you are exposing. So rho r is you will get here. So you'll able to IQ will be modulated by the interference effect between the radiation scattered by the different scattering bodies. So you'll get a high intensity parameter like this, and that's intensity parameter. If you see, you have a smaller particle to a bigger particle here, d. You will see that initially you'll get, if a very small particle, your scattering data is with respect to q, which like this. But when you give more and more size, that q value will is decrease, and you can see that it will decrease. So larger the length scale, so q is proportionally related to pi by d. To characterize size of d, one needs to do a scattering experiment which is the whole q span in the range around q equal to pi by d. So here you can see this is the diameter of the particle. So to get the information large that this information you have to q has to be varied in the relation of pi by d. So larger the length scale, so lower the q you have to come down to get better information. So in general, if you see that scattering intensity is expressed, IQ is expressed in terms of this n number density of particles and into this rho, that is the scattering length density rho, into V volume of the particle V square into PQ and SQ. So PQ and SQ are the two factors here. So that rho generally we express in two terms, that is rho of the particle, rho P, that is scattering length density of the particle minus scattering length density of the matrix or the solvent. So because you have for this X-ray and neutron scattering, and you have to use a particular matrix or the solvent that you use in with respect to the solvent, how the particle contrast varies. So that will express in terms of scattering length density of rho P minus rho M. You will get the where PQ, that is nothing but FQ square, that earlier we studied in X-ray diffraction, that intensity I equal to F square. So here similarly P is called structure factor or a form factor of that, mainly give intra-particle structure within the particle. That information will give the how the particle interacting with particle, within the particle. That information will give, that depends on the shape and size of the particle. It reflects mainly distribution of scattering material within the scattering particles, and it depends on shape and size of the this information we get from the PQ factor. For SQ, that is mainly called structure factor. So that will give interparticle interaction. So one particle with another particle interaction. So it's related to the spatial distribution of the scattering particle in the surrounding medium. If you have a solvent, in the solvent you have a different particles are there. So one particle to another particle, how the interaction is there. So those information you will get. It's decided mainly by interaction with the particles, and you will get a interparticle correlation distance in this case. So mostly, so these two parameters, that SQ and PQ, that you get from the small and X-ray neutron scattering, that will give both shape, size as well as within the particle interaction. So IQ, if you see this equation, in this equation V, P, Q and SQ, if you remain constant, so IQ is mainly related to this parameter, rho P minus rho and rho particle minus rho medium whole square. So this is expressed in terms of contrast factor. If the material is how much that constant that I will discuss. So it depends on that, the variation of the electron density or scattering length density of the particle to the minus the electron density or scattering length density of the medium. So if you see that scattering cross section, that this you will see the scattering cross section of X-rays and neutrons, that I have earlier discussed this also, that in case of X-ray, the scattering length is that his cross section is increasing with respect to the size of the Z electron density of the atom. With the hydrogen, this atomic this is quite low, that scattering cross section is quite low, but in case of cesium, you see that's a heavier element is quite large. But in case of neutron, it's the interaction property of the neutron mainly that randomly varies. For example, you can see that this is generally for all nucleus, that hydrogen is quite large, but in case of lithium is small. So it's a randomly variation. So mainly small angle X-ray scattering, that depends on electron density, or a small angle neutron scattering depends on scattering length density. Both are close related and provide directly complementary information. Like the information you get X-ray and in neutron, they are complementary technique, and both can be used to get better information about the material. If you say the small angle Newton scattering, that scattering length density, if you measure, so you use that is rho equal to summation of Bi by V. So Bi, that express either the scattering length V, which is expressed in terms of 1, that 10 to the minus 2, minus 12 centimeter in that case. So that you see that like hydrogen, it is negative, minus 0.37 to 10 to the minus 12, but deuterium, it is positive. So that's why hydrogen and deuterium mostly used, deuterated solvent is used in case of neutron scattering studies. So if you have a zero contrast, there is no variation between the solvent rho sample minus rho medium is zero. In that case, you will not able to get any contrast variation, and that will not use for this. You will not get any information substance study. So here rho is mainly expressed by Vi. Vi the sum of that scattering length per unit volume that will express here. But in case of if you see in case of this X-ray, this is expressed in terms of here that rho particle minus rho matrix. The electron density is expressed rho equal to Ne by m into D. So D is density of the material. So m is equal to m is number of electron. In case of water, I have taken number of electron here, and then mass of the particle. So you'll be able to get electron density is 0.5 moles per centimeter cube. But that is in case of X-ray, in case of electron density. But in case of neutron, it is equal to this is scattering length density is expressed. So if you see that rho minus rho p minus rho m, that we call contrast, you can see an example I have shown. You have in a green solution, you have put a pink color particles. So initially that particle is here, but you are not able to see the particle. You can't see the particle unless until there is rho p minus rho minus is not equal to 0. If there is a contrast variation between the particle and the solvent, this is the particle. Here the particle you are not able to see. But once you make that very rho p minus rho particle minus rho m not equal to 0, and then only you'll be able to see the particles. That means making invisible to visible by using a particular solvent. That particular solvent you use, that solvent is that scattering length is different from that of particle you'll be able to see. You can see here that you can see the core cell structure. If you want to see both information about core and cell, you design your experiment in such a way that the ones that here is to see the core, you have to that this cell effect has to be nullified. For us to see the cell, the core effect has to nullify. Such that you have to choose a solvent that in the solvent matching, you can say that is matching the scattering density of a molecule with that of the solvent. This facilitates study one component by rendering other invisible. So you want to see the core by making cell invisible, or you want to see the cell, you have to make core invisible. So since hydrogen and deuterium, there one is negative hydrogen, that when scattering length, and deuterium is positive. So mostly that deuterium is used as a DTO, as a major solvent for this type of study. I have just given an example. You can see like this X-ray and neutron contrast things. So if you have a optical rod, so you can the glass that rod I have put inside a solvent, and if your delta Ri, that refractive index, there is no variation in refractive index of the particle of the glass rod and that of solvent. Here you are not able to see this glass rod. So, but here there is a refractive index difference. You are able to see that glass rod. So this is something like the contrast matching. You can say the refractive index matching. So this is the same phenomena used in case of small angle neutron or X-ray scatterings. So you can see here that this is the contrast factor that we call. So to see that you have to make that here the solvent you have to choose in. Initially here you're not able to see the particle inside the solvent. You have to make the solvent slightly different to see the contrast variation. And if you have multiple particles in a solvent, like you have a bigger particle, L11, you are able to see here. But the green one is matching with that of the solvent, you are not able to see here. But here you have matched the bigger one, that scattering length of the bigger particle match with that of solvent. You are not able to see that bigger particle, but smaller particle you are able to see here. But to see both the structure, you have to choose the concentration of the concentration of the strength of that solvent in such a way that both can be seen. That means that in IQ is mainly proportional to this terminology, and to see Here you can see the both core and cell information because the scattering length density of the solvent, core and cell are different. So they are mismatched. But if you have a cell to visible, the solvent to core has to be equal. Then you can able to see only the cell structure. You can see the both red core as well as solvent is same. But to see the core, you have to solvent and cell has to be same, scattering length. The core is visible in that case. So in that way, you have to design your experiment that we have given you an example here. If an A and B component is there, so that you can see the contrast by X amount of that material density with D2O and 1 minus X of water. Like in water, you have to mix the D2O, you have to go on doing experiment and see at a particular concentration, you will be able to see both the components, individual components. By one example here, that silica, 1% silica in different concentration of water and D2O I have mixed. The water is 25% and 75% is D2O, or here is water 50% and D2O is 75%. The black one you can see here how that scattering IQ versus Q, or this is changing with respect to this. And then you can get the intensity by square root of this terminology. Since IQ is equal to this, so if you square root of this, you will get a constant into rho P minus rho S. You can see at a particular, if you go, then it's the scattering length of silica 3.8 into 10 to the power 10. You'll be able to see there is here that is constantly a matching point that is about 62% D2O and D2O you will see the cross section here. So depending on that, you have to tailor your experiment. Similarly, in case of X-ray, you have that IQ is proportional to variation of rho. The rho particle minus rho matrix. You can see here, if a rho particle rho matrix, their contrast is different, then you have to be able to see this both the structure of this image. But if that pink color here, you can see it's matched, that contrast is matched here with that of solvent, you are not able to see that particular image, only this triangle you are seeing here. So the contrast in case of X-ray is mainly caused by the molecule composed of different atoms, like hydrocarbon in water. You have to get surfactant molecules in a water solvent or something, that surfactant nothing but a hydrocarbon chain. In that case, with water and this carbon-based molecule, so they have variation in the contrast. So some molecules, so you can also same molecules can use in different densities, like crystalline or amorphous region. Those things you can distinguish by using this type of X-ray scattering technique. So that this I have already discussed, that how the scattering electron density is measured in case of X-ray. And then the information what you will get from the Newton diffraction or X-ray scattering studies, mainly here in this equation, that IQ equal to n v square into rho p minus rho m whole square of PQ and SQ term. So mainly that PQ and SQ will give PQ is form factor, SQ is interparticle structure factor. From form factor mainly you will get the information about shape and size, whereas that IQ, SQ will decide the interaction between the particle. So that in that a number of particles, you will also get number of density. So this is from the structure factor that the IQ SQ factor will get interaction, the ordering or the shape, size and size distribution you will get from the PQ factors. So all these information will be able to get from X-ray or Newton diffraction, Newton scattering techniques. But here you have a dilute and concentrated system dependent. Like in a solution, you have some particles that highly concentrated and diluted. If it's highly concentrated, then what happens? That particle they interact with each other. But in a dilute system, interparticle interaction is much less. But you have only form factor that you get here. You have the dilute system, that means your D here, that this is the particle size, and distance between two particles is much greater than lambda. You have a path length of the lambda is here. This is the lambda. So here you can see R1 by 2, R1 by 3, and R2 by 3. They are much larger than that of the wavelength of the X-ray or neutron that you use. So in that case, the particle interaction will be very less. Only you will get that form factor. You will get PQ parameter that will give shape and size of the particle. So IQ is mainly here concentration dependent, proportional dependent. So intensity increases linearly with the particle number. So number of particles will increase, the intensity will keep on increasing. But if you get a dense system here, in that case, you can see here lambda is this much, and your particle distance is quite small. You can see here. So distance of the particle is equivalent to lambda, and this distance is almost equivalent. In that case, structure factor, that PQ parameter will predominate, and you will get mainly interparticle interference rather than the shape and size of the particles. Like here, you can see also a dense crystal, a liquid crystal. There were particles here, they are arranged in a hexagonal lattice to form a liquid crystal. Here you can see the lambda is this much, and the particle distance is almost equivalent to that. So you get mainly interparticle interference. Structure factor here. If you see the plot of PQ, that IQ, which is expressed either in PQ or SQ versus wave vector Q, you can see this blue line is PQ here. So PQ is continuously, with Q factor is decreasing, whereas SQ you are getting, peaks depending upon the particle interaction, interparticle interaction. So in dilute system, if a dilute system, mainly that PQ is dominant, that I discussed. So dilute system, the PQ is mainly dominant in that region. But in a concentrated system, that Q equal to 2 pi by D in that range, if you will get a particular peak type structure, so that will give that interparticle interaction in that system. And this, once you get the PQ or Q, that you have to go for a PQ, log PQ versus log Q plot. From this PQ, you have to express in log terminology that I have expressed here, and you have to see how the this you fit a linear line here to this vector, how this decay is occurring. So if it follows Q to the power minus 0 is continuously decreasing, that is constant in this region. So that will Q to the power minus 0, it mainly so the particle is spherical shape. Q to the power minus 1, you will get the particles are cylindrical shape. If it's Q to the power minus 2, that decay, then it is disc shape. Right? So depend also, you can get other information like surface characteristic also from this plot. So mainly this factor you can see here. This is some common example, the study example that I have shown here with silica particles. You can see that PQ and SQ versus Q is for a spherical particle is is symmetrically constant, and then it's decreasing. Even this region, if you plot, it's Q to the power minus Q to the power 0, so that is the size of the particle is spherical, or you can even get some ellipsoid. But with the Q to the power minus 1, in this case, it's mainly that rod shaped micelles. You will get like this plot here, the slope you have to draw here, like in this region, and then you have to able to see this type of here it is Q to the minus 2, mostly disc-like. So these are the silica particle of different structure is formed, or you can also get similar type of spectra in case of surfactants also, depending on the micelle formation. But in this case, in addition to that PQ and SQ, and you will mainly get the information, you get that one is intensity here, that is the IS. So that you have to convert to a Fourier transform. You will get a PR, pair distance distribution function. The PDDF function, you get PR. So that is you need to get Fourier transform to get a real space data. That is that PR is nothing but probability of finding a vector of length R. If this is a total molecule, a protein molecule, a big protein molecule I have shown here, and this is the repeating distance R, that is a vector, this R distance. I want to find out the repeating unit of that vector length R in this whole structure. So the probability of finding a vector of length R between the scattering center, this is one within the scattering center, this is the maximum scattering center. From that, the probability of finding this vector R is decided by the pair distance distribution function. So that you will get just intensity versus that Q. You have to Fourier transform to get a real unit. This type of curve you will get. And so that is mainly that IQ is nothing but scattering amplitude of the from the X-rays from the atom or the from the molecule, and then you have to multiply that IQ equal to AQ into AQ star dash, that is scattering amplitude, and you see complex conjugates. So there, from there you get this type of equation that I intensity is equal to pair function PR into sine SR by SR into PR. So I will not go to the detail that equation you'll find in any X-ray scattering book. So this PR mainly provides that real space interaction of IQ that will intensity you get. So from the PR data, if you will get this type of shape structure, and that will analyze. If you have a spherical, you can see this red one. If a pair distribution is spherical, so symmetrically is there, then you have a spherical particle. But in case of a cylindrical, initially it will be this log normal type initially, then it's decreasing. But in case of you can see that this core cell structure, you can get it's a blue line. You can get, or if you have a double shaped dumbbell shape structure, you can say you can get a two forms here. So this type of pair distribution function will get. So that provide information about the shape of the particle. In this paper is detailed discuss how this PR is related to the shape of the particles. So in case of a SNAS analysis, what you get, but as I told, in case of SAXS and SNAS, the data interpretation is quite difficult. So first, for this analysis, you have to select a model from the available various model. Like you have a core cell model, you have a only that core model, or that you have to single particle model. So those different models are available. So those model you have to choose which one is better fit. So first you have to select a model for the possible structure and interaction, and feed the experimental data using selected model by fixing the known value, whatever the known physical parameter you have. So you have to fix that value to get, if it's good fit, then that will be the probable model to interpret the data. But if you have it's not fitting, then you have to keep on varying to get the possible best model to get the shape size of the structure. So it's mainly you have to go for a complementary technique to verify that. You can see here this is PQ parameter d psi by d omega d epsilon by d omega with respect to Q. If you validate that, then you get a different type of this IQ para factor with respect to rod, myself, and micelles. You can see initially you have a universe like surfactant molecules initially at a very low temperature, like a particular surfactant P85 taken. It is a temperature dependent. It's polymer dependent on the temperature. They form different structure depending upon the temperature of the solvent temperature. So mainly if you say low temperature, that is it's mostly it exists as a monomer. So that means there is no micelles formation. It's monomer. You can see here it's continuously decaying like this. But when you have a micelle formation, scattering density increases. The scattering density also increases here up to this, and then you'll get a spherical micelles here in that case. But once it goes to high temperature, as micelles found in that structure, the high temperature, then it further aggregate to form a cylindrical micelles. So that cylindrical micelle you can see. So here Q to the power 0 and Q to the power -1, those type of relation comes. So as I discuss here, how the Q to the power -1 is rod-like and Q to the power 0 is sphere. That you have to see in this thing, this data, and you can see what is the shape of the particle that structure is formed in this case. This is another example of the SNAS study of the micelles. You can see where you have to theta, HDS, sodium rhodocyl sulfonate, DTA, and C12, E10, different surfactant that have taken. And here this surfactant form different types of, here you can see different types of structure it formed showing. So from that you can calculate that polydispersity as well as aggregation number, how many surfactant aggregated, and you can find out the SMME and major axis that both whether it's a spherical or cylindrical elongated shape information you can also get. Similarly, this is a ferrofluid that are Fe3O4 nanoparticle in water. By using water DTO matte solvent, you can able to see both particle as well as cell information. That here that the normal light scattering measurement that you use dynamic light scattering. So that is to give overall particle size. Whereas in small angle X-ray scattering, you are able to size of the core. You can see the core 4.8 nanometer that you are getting here. But in the SNAS study, you get the particle size and the thickness both. So both particle size of the thickness here, you can see you are getting up about 4.8 core nanometer, and cell 4 nanometer is a total about 9.8 nanometer. But in DLS, you are getting both core and cell is about 10.5 nanometer. So this almost getting in the both core and cell information using this type of study. But if you see both SNAS and SAXS, they can use as a complementary to support each other. Here, in case of SNAS, the signal can assess the contrast between the solvent and that of hydrocarbon chain of the core and the micelle. So you can see that two subparameter, one is C-type, cetyl ammonium chloride, and this is C-type, cetyl tetramethyl ammonium bromide, cetyl tetramethyl ammonium chloride, and cetyl tetramethyl ammonium bromide. One case it is chlorine, then head group, one case it is bromine is head group. You can see in case of SNAS spectra that you are getting only a symmetric peak in case of SNAS data. But in SAXS, you are getting a peak with a head with a slightly asymmetricity here, a hump is here. So if you see here, so there is a hump in this case of SAXS spectra. In case of small angle X-ray scattering, that is because in case of neutron scattering, that mainly scattering length density, it depends. So there that you are mainly seeing that the information of the core that you are getting here, that hydrocarbon chain information you are getting in this area, but whatever that cell one, so that information you are not getting here. But in case of SNAS, you are not getting. But X-ray, you are getting both core as well as that say this formed like some sort of this head group is like this. So this type of micelle if it formed, so that this is you have a head group of chloride or bromide here. So those information you are getting in case of small angle X-ray scattering, or other hydrocarbon information you are getting from the Newton scattering. But that is more predominant when you have a bromine, because bromine as in X-ray is high electron density compared to that of chlorine. Because of high electron density, you can see there is clearly two doublet peaks you are able to see here in case of SAXS. So similarly, you have a core cell structure like some gold nanoparticle coated with some organic molecules. So like oleic acid or some other surfactant molecule coated on that gold nanoparticle. So from the SNAS, you can able to get the cell information that mainly the coating things. But in case of X-ray, you can able to get both core as well as the cell information. So these are both complementary technique to each other. So if you see that we have a national facility at neutron scattering measurement at our Dhruva reactor, that from anybody from within BIS or outside, they can approach to the concerned person in the here National Facility Center, so they can turn their Newton scattering here. In this case, mainly we have that wavelength is in the range of 0.01, Q range is 0.015 to 5 angstrom, and you have a del lambda variation is very small. That variation in lambda is quite small, and you have a linear detector, position sensitive detector. In that case, you can see here you have an image that says that neutron source is coming, and then it collimated with the potential before it falling into the sample, and there is the sample, and it fall on the sample, and it go to the detector to get the analysis. So mainly this reactor is a vertical tank type reactor. The natural uranium is used as a source. So the Newton loss is 1.8 into 10 to the power 14 Newton per centimeter square per second. So that used in case of this facility. Then we can approach the concerned person to get their Newton diffraction studies. So here, if you have any questions, so we can discuss on this part, small angle Newton scattering and X-ray scattering, and then we'll go to the second part, that is optical and electron microscope. If any question, you can raise. Okay, if there is no questions, then we can go to the second part. That will be, on this optical and electron microscopes, the basics of the microscope we'll study today, and then the next class will discuss about scanning electron microscope and small and transmission electron microscope. So far what we have studied is based on scattering techniques, either X-ray or neutron scattering techniques. So that will give information about the shape as well as size, but that data interpretation is quite difficult as compared to other techniques. But in case of the optical electron microscope, what you will see, you will be able to see directly the visual data of the directly. You can see the size and all those shape of the particles by using microscopic technique. So if you see, mostly the microscopic techniques that determines the structure of the matter, that will be shape and size. If you see that generally XRD that gives crystal structure of you have a very D value is quite low in that case. That information you get in the crystal structure you'll be able to get from the XRD. But in microstructure, mostly optical microscope, SCM or TM, you will be able to get information about grain, different grains. You have multiple grains, those shape and information, pores information, as well as different component information you will be able to get in that case. So fracture mechanics, that mostly you will be able to get so topographic image you will get in case of microscopic technique. If you see that atomic scale mostly used for structural determination by XRD or by this, but in case of microscope or mesoscopic microscopic both technique, it's quite in this range you will be able to see the microscopic technique. So if you first coming to microscope, so microscope is mainly comes from a Greek word that is a micron, that is small, and a scopus, to look. So using these two words, the word microscope was, and it's used mainly viewing object that is too small. You have to see the small object, you have to magnify it, and that particular magnification where you can able to see that that particular object. That's why it's called, the technique is called microscopic technique. So normally microscope, you can two types of microscope that we have seen. That one is simple microscope, one is compound microscope. Again, in case of simple microscope, it's normal use, and you can see very small objects in that. So in compound microscope, it's mainly two types. One is light microscope and is electron microscope. So light microscope is mainly based on four techniques. One is phase contrast, that you can see the topographic image. One is if you have a fluorescent molecule, so that can be used by a fluorescent microscope, or you can use a dark field or bright field images using this light microscope technique. But in electron microscope, mostly use electron as a source. Here in case of light microscope, visible light or those who are UV ultraviolet light, those are used as a source. But in case of electron microscope, you can use electron as a source. So that is, you can give a scanning electron microscope, transmission electron microscope, or you can use a confocal microscope. So if you see the different terms used in microscope, when you come across the microscope, you will see the first word, that is magnification. What do you mean magnification? Magnification means the degree of enlargement of a particular material. So to see a particular small object, you have to you have to magnify it. So that depends upon the focal length of the objectives and magnifying power of the eyepiece. Since in a lens you have a objective lens, you have a magnifying lens, and so different lenses are there. So you have to depend upon the focal length as well as the magnifying capacity of the objective lens. And then you have two image, you want to see differentiate between two images. So that will be expressed in terms of resolution. That's the ability to reveal closely adjacent structural details as a separate entity. So you have here you have a spot here, and you have a closed space cross each here. So you want to see the resolution of that. You can see how the ability to resolve these two structure. So if that depends on the resolution of the microscope, and you have a limit of detection in the microscope. That means that minimum distance between two visible objects there can be separated. Like like this resolution that we express in terms of limit of resolution, like up to certain length scale, you can able to separate. Beyond that, it's not possible. So that is the limit of resolution, which expressed the 0.61 into W by numerical aperture, the wavelength of that light source used by numerical aperture, that NA. So you will be able to limit of resolution. And then numerical aperture is the nothing but the ratio of the diameter of the lenses of its focal length, that NA equal to N sin theta by 2, where refractive index N equal to refractive index and theta is the angle of aperture. So from there you will get that is the ratio of the diameter of the lens to its focal length, expressed by numerical aperture. And then you have a working distance. You can see here you have a surface you want to see, and that surface, the particular this is the focusing plane of that objective lens. If you see here, this is quite high and this is quite close to the object. So that the distance between the front surface of the lens to the object is decided the working distance. We are varying the working distance close or far. You can see the better resolution image or better contrast quality image you can able to get. Depending upon that, if you see the conventional microscope, in case of conventional microscope, what happened? You have a microscope here, and you have a use either convex or concave lens, and then you have an objective plane here that one side, and you have an image plane on the other side, and the image is always on the other side of the focal plane you get. And you can see here, if you see the object is here, or object is the object is mainly here, and then depending upon from the object is here, the light beam is falling on the lens, then you can get a inverted image here in this case. So that if u is the distance from the object to the lens, and p is the distance from the image from the object, that 1 by u plus 1 by p equal to 1 by f, that we know this is the common lens equation. The magnification is expressed as v by u, that distance between the ratio of the lens to image to the ratio of that of lens to your source. So if you see that it's how the image formation conventional microscope, in sending photographic image, you can able to have an object and you will get an image very close to the lens. Similarly, in photography, you will get an image which is mostly inverted image. In eyeglasses, you will also get an inverted image. Similarly, in microscope, you can see, but here the image size in case of photography is quite small, and then eyeglass is almost equal. But in the microscope, you are getting a magnified image in case of microscope. You see that mainly the optical microscope, you have a light source at the top. This is the light source. Then that is called illuminating system, the radiation source, and you have a condenser lenses are there to focus. The light is coming here, then it is falling on a lens, and that is illuminated to fall on a specimen. Here you have a specimen. On the specimen surface is fall, and then it passes to the objective lens and different eyepiece, and you'll be able to see this type of image from the eyepiece. So you have the illuminating light source, and you have a sample stage here that's situated between the illumination part and the imaging part, in between this imaging lens and the image plate. So then you have that image plate, imaging system, which mainly you have an objective lens that to focus the beam. You have an objective lens here that this is the image part. That objective lens again focus the beam passes through the sample to the intermediate image, and then you have a projector lens, that is a lens projector lens, to get a magnify a portion of the intermediate image to get a final image. So in this case, you have a recording system that converts radiation into a permanent image. So mainly this type of optical microscope, you have a objective eyepiece here, then you have a sample stage here, then you have various objective lens like 10x, 20x, or 5x, depending upon your use. You can exploit that, and you have a focusing axis here that you can use to focus the structure. So in optical microscope, you have sample preparation is quite easy in comparison to electron microscope, which is sample preparation is tedious, but here it is quite easy. It's simple. You would make a flat sample. You can use it, optically finish that. You have to clean it properly, or you have to polish using different carbon papers to make a polished sample, and you can see the structure, or if you have some dents, so that can be removed by etching to reveal the detailed structure. You can see here, you have a chemical etching removes material from the surface at different rates. You can see this is a brass one, first one. You can see different distance for inside that grain structure here, composition, and stainless steel. You can see from niobium, you can see how the structure is different inside that. So those, quite larger scale that you can able to see, that the scale length you can see up to 20-50 micron, that in scale length is here. So you have to see the bigger structure, those things you can see in optical microscope. You can see here you have a bronze revealing cast dendritic, which is a bronze material that here you can see the dendritic structure of that bronze cast. Those things are revealed by optical finishing of that film, that bronze metal. In optical microscope, you can see how this algae or fungi grows on a particular substrate. It's a substrate. On that substrate, you can see how the algae are grown. So those information will in aluminum silicon alloy. In the alloy system, you can see able to see different phases in this type of optical microscope. But with this optical microscope, it's not that is not that much useful. 1 minute. Okay. So this optical microscope is not can be used for a smaller size particles. If a bigger size particle of your you can be able to use that visible light or that wavelength, particular that wavelength is suitable. You can able to measure that size. But you have a smaller structure, so those things you can not able to see using optical microscope. You have to go for a electron microscope, because that electron has much shorter wavelength than visible light. And this allows electron microscope to produce high resolution images than the standard light microscope. Hence, that in case of electron, you can able to vary the wavelength from 0.002 to 0.1 nanometer, depending upon the energy of the electron. Since you have a variable lambda value here, so you can able to see much smaller structure by using electron microscope. That electron have strongest interaction with matter of any radiation. So many types of information is available. This optical that you use visible light, that interaction of the visible light from the top surface only, you're not able to see, you're not able to get much information from the optical microscope. But in case of electron being a shorter wavelength, as well as it's highly interacting with the material, you will get better information of the material. And also it has high intensity and high energy. Beam of electrons are relatively easy to generate. Like you can even go for high energy electron beams, so that will give better information about the structures, and it's used. It can be used in conjugation with a variety of ancillary techniques. Like say, the optical microscope is able to see only the optical structure, that is the topographic image. But in case of this electron microscope, like for example, in scanning electron microscope, we are able to see the composition analysis by using how the X-rays are produced, by using the EDAX facility, energy dispersive X-ray facility, there, or you can also, in case of TM also, transparent electron microscope, then use that facility also. So it is used in conjugation with variety of ancillary techniques, like thin sectioning is possible here, immunolabeling is here, negative staining. So those things can also possible to answer specific questions. For example, if a biological molecule, so that contrast is quite low in case of biological molecule, and also the electron, high energy electron, that biological component may be destroyed. So you can use a negative staining in that case to see the structural information. So you have different facilities nowadays available with preserving the structure in cryo environment to see those type of particular features using electron microscope. So if you discuss coming to electron microscope, that mainly depend upon the interaction of electron beam with a specimen. So this I have already discussed that you have an electron signal that is coming from here. So when electron beam is here, when that electron beam come and fall on a particular substrate, here you have an interacting volume. So in that interacting volume, that depends upon how the material, that whether it's low jet material or high jet material, and also the kinetic, that the energy of the incident electron beam, as well its intensity of the beam. So once that electron beam falls on the sample surface, what will happen? So you have multiple processes can be possible here. So that electron can be returned back here. So that will be a backscatter electron that I have discussed. So that the incoming electron, after interacting or after falling on the specimen, and if that electron is coming back, from they will get a backscatter electron. So that is little higher in that case. So you'll able to, if you have a interaction volume for here, that electron beam. So mostly backscattered electron after falling the electron beam here. So backscattered electron will be up to this distance will come. Here this is the mostly backscattered electron. You will get able to get backscattered electron about 10, more than 10 angstrom distance. So here this is 1 to 10. So after that, you will able to get from backscatter electron. So that is one electron. Another electron is that second electron can produce a second electron from the top surface. So from this surface, you are able to get an electron that is called secondary electron. So this second electron also you can produce. So in case of scanning electron microscope, so these backscatter and secondary electrons are used in case of scanning electron microscope. Use a source that both information will get from backscatter and the secondary electrons in case of scanning electron microscope. So mostly backscatter gives topographic information, and secondary electron also you can use contrast as well as both topographic information that you can use in case of scanning electron microscope. But during this interaction of the electron with the metal, it can produce, say X-rays can be produced. So those X-rays can be a fluorescence X-ray, or so that you can use that X-ray using a SCM facility or TM facility, of EDS, energy dispersive spectroscopy. So that what is the K alpha or K beta you are K alpha or L alpha you are generating here. Those K alpha, K beta can be used to analyze the elemental composition of the particular sample. And in addition to that, during this process, on the electron beam falls, also some, say, Auger electron can be generated, and that Auger electron can be used for Auger electron spectroscopic analysis that we discuss later in last lecture. So in addition to that, some luminescence properties is generated, like cathodoluminescence, you can use them, cathodoluminescence studies. And also, some electron can be transmitted without interacting with the system, or after interacting, it can lose some of energy and transmitted. So those electrons, like one will be inelastic scattering, one is elastic scattering. So that means one is case of energy will be conserved, and elastic scattering, no loss of energy. Yet is elastic, you have a loss of energy occur. So here that this in addition, some electron will directly pass through. So those electrons will be used as a transmitted electrons. That is the basis of transmission electron microscope use. So whole this interaction of electron beam which used for whether producing backscatter or secondary electron or transmission, that is the basis of electron microscopic technique. And in case of elastic scattering, what are the energy loss here? So that energy loss can be used to generated like information from that electron energy loss spectroscopy. That's part of a TM. So from that you can able to get how that information about the bond structure or coordination number, those things, oxidation states, those things information can be get from yields analysis. So overall, its whole thing is that interaction is based on the electronic properties of that material. So you will be able to get the whole information about the whole SCM or TM based on these two studies. From the today's lecture, what we have studied, so mainly two techniques to study. One is small angle scattering techniques, another is a little bit about 11 microscopic basis. So here, that whether it's small angle X-ray scattering mainly, either it may be X-ray scattering or it may be a neutron scattering. So both will give the information about the structure and dynamics of the particles. But in case of wide angle XRD, that we use here, that power diffraction XRD or single crystal XRD. So those give the crystallinity or amorphous information about the D equal to quite small here, because here Q vector is quite Q vector is small, but whenever low high angle is high here, but low angle that theta is less than 10 degree. So there you will get large structure information. Here the size about 1 to 100 nanometer. And there you have a two terminology come. One is PQ factor, one is SQ factor. That one is give form factor, that is the PQ factor that will give you particle shape and size, whereas SQ factor that will give information about interparticle, intraparticle interaction. So those information you will be able to get. So mainly SAXS provide information about microscopic length scale of size about 1 to 100 nanometer. So for that you use scattering techniques. But for diffraction techniques, you will get smaller structure than less than 1 nanometer. And in a scattering, we'll get the information about the bigger structure. So the SNAS data, small angle X-ray scattering data, analysis depends on the diverse set of approximation and models. Like in case of X-ray diffraction or imaging technique, it's directly you will get interpret data, you will get the results. But in case of small angle X-ray or neutron scattering, you have to use various models and approximation to get to transform the Fourier data to the real space, and finally you get the result. But in case of small angle X-ray neutron scattering, you have a variation between that rho solvent, the sample minus rho solvent or matrix. That is the contrast variation you have to see between the sample and the solvent or the matrix to see the structure, that making invisible to visible, that you have to choose a particular concentration or particular solvent where your matrix were unable to see the structure. And both neutron and X-ray are complementary techniques. So they give complementary information. In case of neutron, its scattering length density that decides the whole scattering properties. Or in X-ray, it is electron density that decides the scattering capability of an X-ray. In addition to that, we have studied a little bit about the microscopic techniques. In that microscope, we talk about when the optical microscope. So in case of optical microscope, you can see the larger object of the order of wavelength of that of light. But in case of electron diffraction, that is, you want to see smaller size objects, you can't see those objects using that simple or light microscope. You have to go for electron microscope, because electron microscope has high energy. That means your wavelength is very, very small. So 0.002 to 1 nanometer, in that range you can vary. For example, if a 200 keV transmission electron microscope, the lambda is equal to 0.0025 nanometer. So you can see such a low wavelength you can able to get in a case of electron. So that's why you can able to see even a smaller size of particles. And then that you have electron has quite high energy. Because of high energy, you can get by varying the intensity, you can get high resolution images. And in addition, you can able to get other complementary technique can be merged with that electron microscopy. So you're able to get better information about the structure. For instance, you can get the chemical composition by using EDAX facility of the SEM or TM microscope. Even nowadays, that my electron microscope, that is especially transmission electron microscope, is coming with a knife. You can also cross-check a particular particle and see the internal feature. But those type of information we're able to get from electron microscopy. So overall, so far what I have discussed in my last, including this lecture, last 3 lectures, we have discussed about different X-ray based techniques like X-ray diffraction, proton X-ray diffraction, as well as this single crystal diffraction, and then neutron diffractions, and the X-ray fluorescence spectroscopy, and the PDS and EDAX, SNAS, that XRF, PDS, and XR wavelength dispersive and energy dispersive fluorescence analysis. And in addition to that, today we discuss that two small angle X-ray scattering technique, Newton scattering and X-ray scattering, and then we will discuss a little bit about light microscopy. In next class, we will discuss about transmission electron microscope and scanning electron microscope, and how these techniques are used to get the image for the instrumentation part, and then the imaging technique as well as that we'll see how to interpret those data from SCM or as well as TM, how the information we get and how to interpret, especially in TM data, how to interpret the particle size, particle shape, as well as you can able to get that diffraction pattern, electron diffraction pattern, those analysis you can able to get. So if there is any questions, you can put here. Okay, there was a question on what is the difference between what is the difference between an Auger electron and a backscatter electron? First of all, the backscatter electron is the same electron that from the source it's coming and interact in the sample, and that electron is getting back. So that is your backscatter electron. But in case of secondary electron, that electron is getting absorbed, or even it can produce another electron from the top surface, that is secondary electron. That you can say it's a simple photo electron that's coming out from the sample. But Auger electron is a 3-electron process. Like if you see that, can I see that slide? If you see that, I can draw it. Okay, if you see that this is of a electron, that this is of the nucleus, and one electron is here, and then you have a K cell, and then you have a L cell, another electron is here, and then M cell is there. So when an X-ray beam falls on this, and that electron is coming out, so this space will be vacant. So now this electron moves, and here you have a vacant site. To the vacant site, so this electron, higher energy electron, it will fall here. So once it falls, so you will get some sort of X-rays you will get. So in that X-rays will produce. If that energy is sufficient enough, and this is enough, so here instead that X-ray can able to here that once this electron will fall here, so you'll able to get another this will be now filled, and you will have a vacant space here. So that vacant space can be filled by another higher electron is coming here, and you will able to get during this process you will able to get that electron, release of electron, that is called Auger electron. So that I will discuss in detail when I'll go for the Auger electron spectroscopy and this X-ray photoelectron spectroscopy that I'll discuss. So mainly Auger electron is a 3-electron process, whereas in this second backscatter electron is the same electron that will come out. One more question. There is one question only, or only one? Okay, if there is no more question, then we'll stop today's lecture here, and Friday we'll discuss about scanning electron microscope and transmission electron microscope. So 2 microscopic techniques we'll discuss in the next class. Thank you.